A software defect is discovered in the network, and immediately the process breaks down. The bug report bounces between teams, generating instant friction between the developer who wrote the code and the quality assurance tester who broke it. The arguments are almost entirely subjective. The developer insists the code works flawlessly on their local machine, or they claim the abnormal behavior is actually an intended design feature. Talented engineering teams find themselves paralyzed here constantly. This gridlock occurs because the organization is relying on verbal debates to solve technical problems, operating in a structural void without a formal communication protocol. The internationally recognized ISTQB standard for test management outlines a definitive architectural solution to this exact bottleneck. Effective defect management replaces these subjective arguments with a state-driven protocol, focusing the team on the technical lifecycle of the bug rather than the intent of the author. By enforcing a rigid state machine, organizations eliminate ambiguity over who owns a problem, accelerating release cycles and stopping the ping-pong effect before it starts. We have to map a defect's exact journey from the second it is identified to the exact moment it is eradicated from the system. We establish the absolute boundaries. Initial discovery sits on the far left, final resolution sits on the far right. A developer assumes responsibility for the open ticket and begins active code investigation. The state officially shifts to in progress. The defect is actively being worked on. The developer identifies the root cause, writes the patch, and merges the new code into the main repository. The developer advances the ticket to resolved. This is where strict role separation applies. Developers cannot verify their own fixes. It invites confirmation bias. Only a dedicated tester can execute the final verification and push the state to closed. We also have to account for false positives. A reported bug might be a duplicate ticket or an intentional design choice mandated by the product owner. For these cases, we build a rejected pathway directly out of the open state. If a defect is marked resolved, but the tester proves the patch failed during final verification, the workflow must enforce a penalty. A reopened accountability loop forces the ticket straight back to the developer for a second attempt. Closed remains the singular termination point. When a ticket arrives here, the tester attaches a specific resolution reason to ensure the metadata can be extracted cleanly later. This explicit visual workflow guarantees that at any given microsecond, the question of who owns this defect has an undeniable binary answer. The state machine will immediately fail if the engineering team feeds it ambiguous or incomplete data during the process. Consider a catastrophic technical failure that has almost zero impact on the actual user base. A total system crash on a legacy IE11 browser is massive severity, but because fewer than 0.01% of users access that environment, the business assigns it low priority. The opposite extreme is a harmless glitch posing an immediate threat to the brand's reputation. A typo in the CEO's name on the landing page breaks zero code, meaning low severity, but it's a public embarrassment requiring high priority execution. Decoupling severity from priority ensures developers don't waste sprint cycles repairing invisible system crashes, while massive branding errors remain live on the site. As a project approaches its release deadline, the scope scales up from isolated bugs to hundreds of defects accumulating simultaneously. The organization convenes a defect triage workshop, a cross-functional governance board designed to filter the massive backlog. Triage determines a bug's fate by measuring it against 3 uncompromising constraints: business benefit, product risk, and resource cost. Fast-moving Agile teams typically resist this formal triage. They prefer to bypass the documentation entirely, addressing bugs verbally during daily stand-ups. Skipping formal documentation for sprint-blocking bugs or cross-team dependencies generates untraceable technical debt. The absolute limit of organizational friction occurs in a hybrid environment, where iterative Agile teams must share a codebase with rigid Waterfall vendor teams. The architectural mismatch is severe. Agile operates in rapid, circular iterations. Waterfall operates in a slow, linear sequence. The Agile side manages defects in Jira. The Waterfall side tracks them in massive Excel spreadsheets. The data fractures into isolated silos, destroying release alignment. The technical fix requires utilizing webhooks and REST APIs to establish bidirectional automated synchronization. Glowing data pipelines bridge the gap. A state change in the Agile sprint instantly updates the Waterfall registry. The procedural fix is mandatory cross-attendance. The Agile product owner must sit in the Waterfall triage meetings to manually synchronize defect tolerances. Scaling a massive product requires synchronizing the underlying engineering philosophies. Otherwise, critical failures get lost in the translation between teams. Moving a defect to closed triggers its final transformation. It becomes the raw metadata used for pipeline analysis. An archive of thousands of accurately categorized closed bugs acts as a diagnostic X-ray for the entire software engineering department. We evaluate the organization using phase containment efficiency. This metric measures the team's ability to catch a bug in the exact phase it was created. This chart shows high phase containment efficiency. A massive volume of defects is isolated and resolved entirely within the design phase. Erasing a design flaw on a whiteboard costs fractions of a cent. Patching that same flaw after a live production deployment burns immense capital. High containment efficiency directly reduces the cost of quality. We audit developer performance by querying tickets trapped in the reopen state, exposing exactly where inadequate unit testing is failing the pipeline. The location metadata reveals defect clustering. Mathematical probability dictates that 80% of your bugs are hiding in 20% of your codebase. The heat map visualizes the spatial clustering. The majority of the failures are concentrated tightly inside a single, highly complex, isolated module. Quality assurance leads leverage this spatial data to force product owners to allocate the next sprint entirely to refactoring that toxic sector. The ultimate directive is shift left, using historical failure data to move quality assurance so far upstream that defects are blocked from injection in the first place. Defect tracking is an objective process. It is a system built to trace logical outcomes, not assign blame for broken code. By strictly enforcing lifecycle states and analyzing the resulting data, engineering teams use the history of their mistakes to build a roadmap for systemic reliability.